Okay, so let's start today's lecture, and we'll just continue with what we have been doing last lecture. Okay, so we've been talking about second order linear constant coefficient homogeneous equations. Okay, so and such equations are going to take the form ay double prime plus by prime plus cy is equal to 0. Okay, so it's just like what has been shown here. Okay, so what has been shown here. Now with that equation, we've been talking about characteristic equation. So this is the characteristic equation. Okay, so it's the characteristic equation. Now the characteristic equation AR squared plus BR plus C simply inherits ABC, the constants ABC, from the ABC in the equation. Okay, so from the ABC in the equation. And then we're going to work out the roots. Okay, so we're going to work out the solutions of this quadratic equation in the cases when the discriminant is positive. If the discriminant is positive, you're going to have two real distinct roots. And if the discriminant is equal to 0, you're going to have two roots that are equal to each other. Now, we've been talking about the case when the discriminant is negative, right? So if the discriminant is negative, you are going to have two distinct solutions, and they're going to be in the form of complex conjugate roots. Okay, so that's kind of what happened here, is that they're going to have a common real part minus b over 2a. There's a common complex part square root of 4ac minus b squared divided by 2a, so common real and common complex part. So the solution is looking like lambda plus minus I times mu. Okay, so that's complex conjugate roots. Now in the complex conjugate case, okay, so we've been talking about the Wronskians, right? So, and fundamental solutions. So the two fundamental solutions are going to take the form. So here, the slogan, okay, so I would say the slogan, okay, so slogan is going to say that the real part, okay, so real part, okay, so enters the exponential. Okay, so the real part enters exponential and complex part, right? So the imaginary part enters sine and cosine. So that's kind of the slogan, right? So it's the slogan of solving this kind of complex conjugate case, right? So the real part enters exponential means that the common real part lambda, which is the lambda here, right? So the lambda here or the lambda here, the common real part of the roots, right? So you have a pair of complex conjugate roots, which means that lambda is going to be the common real part, is going to enter the exponential, and complex part is going to enter sine and cosine. So the mu is sine and cosine of the complex part, which is the mu here, which is the mu here. So the complex part enters sine and cosine. So the real part enters exponential, and the complex part enters sine and cosine. The solution is going to be a linear combination of e to the power of lambda t cosinuses of mu t and e to the power of lambda t sinuses of mu t. So that's a linear combination of these two solutions. Okay, so that's linear combination of this solution. So that means the y of t is c1 e to the power of lambda t of cosinuses of mu t, right? So plus c2 e to the power of lambda t of sinuses of mu t. So that's kind of the general solution for the complex conjugate case. Okay, so complex conjugate case. Now, in order to have this y1, y2, right? So suppose this is your y1 of t, suppose this is your y2 of t, you just want to take the Wronskian of w of y1, y2. Okay, so by the definition of the Wronskian that we talked about last time is y1, y2, y1 prime, y2 prime. You will check that this is non-zero. I will leave it to you as a homework exercise. Okay, so you can check that this object is just non-zero. Okay, so that's kind of the thing. Okay, so let's look at a few examples just to get familiar with all these issues. Okay, so for example here, it says that can you find the general solution of y double prime plus 4y prime plus 5y is equal to 0? Okay, so that's kind of the example 1. Okay, so example 1 is this equation y double prime plus 4y prime, right? So y double prime plus 4y prime. Okay, so plus 5 times y. Okay, so plus 5 times y is equal to 0. So the solution is going to have the root r squared plus 4r plus 5 is equal to 0. Okay, so that's the root, the characteristic equation. Now you solve this characteristic equation. So r12 is equal to minus 4 plus minus the square root of 4 squared is 16, right? So 16 minus 4 times AC. So 4 times 5 divided by 2. So that's going to be minus 2 plus minus. So this is 20. So that's 2. So that's I. Right? So that's kind of the things, right? So that's because the 16 minus 20 is equal to minus 4. And therefore, the square root of minus 4 is like 2 times I. Right? I squared is minus 1. I squared is minus 1. So that's, you have 2 times I divided by 2. So that's I. So the lambda, you have to recognize that real part is minus 2. Common complex part is 1. Right? So common complex part 1. So the solution is going to take the form C1 e to the power minus 2 of t cosinuses of t plus C2 e to the power minus 2 of t sinuses of t. So the common real part enters the exponential, and the common complex part enters sine and cosine. So that's what you have to remember. Okay, so that's what you have to memorize. Common real part enters the exponential, and common complex part enters sine and cosine. Now the question comes here is that, can you take mu equal to minus 1? Right, so this is a plus minus, but it doesn't matter which one you take a plus, you take a minus, right? So it might well happen that I'm going to take mu in minus mu instead of mu. Does it really impair my solution? Well, if mu is minus 1, you're going to have a solution y of t is c1 e to the power minus 2t of cosinuses of minus t, right? So plus c2 e to the power minus 2t of sinuses of minus t, right? Sinuses of minus t. And therefore, cosine minus t, this is c1 e to the power minus 2t of cosine t minus c2 e to the power minus 2t of sine t. So you can see that the solution looks like different. But in terms of general solution, it doesn't really matter because the plus c2 and minus c2 are both constants. So it doesn't really matter which one you take a solution. Either is good. Usually you want to take the positive one. Right, so it's just a common sense, more common sense that you take the positive one. If you take the negative one, you're kind of violating like the common sense, right? So it's it will take the grader a little bit more time to recognize that you are actually doing the negative side, right? So that's kind of, you want to be more of a common sense. Okay, so that's kind of the thing about this complex case. Okay, so complex conjugate case. Okay, so that's kind of the thing. Okay, so let's work out another example. Okay, so here's one more example. Okay, so this example says that, can you find the solution of an initial value problem? Okay, so that's a nice initial value problem. You want to find a solution, right? So solution of this problem, the problem is okay. So the second example. Okay, so the second example says that you're going to have an initial value problem of the form 16y double prime minus 8y prime plus 145. Okay, so 16y double prime minus 8 of y prime plus 145 of y is equal to 0, right? So it's equal to 0 with initial condition y0 minus 2, y prime 0 is 1. Okay, so that's y0 is minus 2. And y prime 0 is equal to 1. Okay, so we want to solve this equation. How do you do that? Well, we start from the characteristic equation, 16r squared minus 8 times r plus 145 is equal to 0. You want to solve for the r, right? So how do you solve for the r? Well, the r12 is equal to minus b. So 8 plus minus the square root of, okay, so square root of b squared of 64 minus 4 times 16 multiplied by 145 divided by 2 times 8 is 32. So that's the, it looks like there's a lot of calculation here, but you must notice that 4 multiplied by 16 is equal to 64. So this is actually essentially 8 plus minus the square root of 64, right? So multiplied by 1, so that's kind of 144 with a minus sign divided by 32, right? So that's kind of the way how you cook up a solution. So that's 8 plus minus 64 is 8 multiplied by 12 multiplied by I divided by 32, right? So that's kind of solution. So the solution is going to be 1 over 4 plus minus 1 over 4, so 3 times I. That's the common real and common complex part, right? So that means common real part is 1/4, common complex part is 3. That's how you cook up solution. So the solution, general solution, so that means the general solution, okay, so the general solution are going to take the form y of t is c1 e to the power, okay, so e to the power of 1/4 of t multiplied by cosine 3 times t plus c2 e to the power of 1/4 of t, right? So multiplied by sine times 3 times of t. So that's going to be your solution, right? So that's going to be a solution. Now you have to put initial conditions there in order to determine those undetermined constants, right? So the initial condition says that y0 is -2, y prime 0 is 1. So the y0 is -2 is going to tell you, right? So if you take t equal to 0, so c1, this is 0. If t is equal to 0, so that basically e to the power 1/4 multiplied by 0 of cosine 3 times multiplied by 0 and plus c2 e to the power of 1/4 multiplied by 0 multiplied by sine 3 times 0. So that's all zeros. And this is equal to what? This is the sine 0. This is sine 0 is 0. So we have nothing here. This is 1. Cosine 0 is 1. So that's just c1 is -2. So you get your c1. And what about y prime of 0? Well, in order to calculate y prime of 0, y prime of 0 is equal to 1, right? So that's going to be y prime of 0. You have to really take a y prime of t, right? So y prime of t evaluated at t equal to 0. So that's y prime of t is a c1. Okay, so multiplied by 1/4 e to the power of 1/4 of t of cosine 3t. So that's a product rule, right? So that's a product rule. So that you're going to have plus c1, right? So e to the power of 1/4 of t. Then cosine 3t is 3 times sine 3t with a minus sign. So this plus sign is actually a minus sign, right? So this plus sign is actually a minus sign because you want to have minuses here. And then it's going to be plus c2 of 1/4 e to the power of 1/4 of t sinuses of 3t. And then it's going to be plus, right? So plus c2 e to the power of 1/4 of t, right? So, and then it's 3 times cosine 3t. So that's kind of the derivative. So you have to really take the derivative carefully and evaluate t equal to 0, right? So if you evaluate this at t equal to 0, you're not going to have this term. You're not going to have this term. And all these terms are going, so that's going to be c1 over 4. T equal to 0, this is 1. T equal to 0, this is 1. So that's c1 over 4. And then plus here is going to be 3 times c2. And this is 1. This is 1. So this guy is going to be 1. Right? So that's kind of a lot of things here. But indeed, in the end, it's going to tell you that c1 over 4 is equal to 1. 3c2 is going to be 6. Right? So plus 6 is 7. So C1 is 28, right? So C1 is 28, right? So C1 is 28. So that's good. So sorry. So here I have 1 over 4 C1 plus 3 C2 is equal to 1. Okay. So okay. So here is I have to calculate this. C1 is -2. Sorry. So that's kind of going to flip things around, right? So that's not going to really take your C1, but here it's going to be here. Here is C1 is already known, right? So C1 is -2, so that's kind of -1/2 plus C2 multiplied by 3 is 1. So C2 is equal to what? C2 is equal to 1 over 2. So C2 is 1 over 2. So the solution is actually C1 is equal to -2, right? So C1 is equal to -2. It means that we don't need this C1, C2, right? So that's instead of general solution, now it becomes a particular solution, right? So particular solution where C1 is being determined -2, C2 is 1/2, right? So C1 and C2 are both being determined, right? So that's kind of the solution, right? So that's kind of solution. So this is really kind of examples where you solve for complex conjugate roots, right? So very important thing is that everybody have to memorize this formula that this is real part. Okay, so common real part is going to enter the exponential, and common complex part is going to enter the sine and cosine. So that's kind of a common as a slogan for this problem, right? So if you memorize the slogan, it will be easy for you to memorize the formula. Okay, do not try to memorize the formula before you know the slogan. Okay, the slogan will be the crucial thing here. Okay, so that's kind of the, the thing. So here I have we have been preparing such a formula sheet for you. Okay, so remember this is not going to be provided on your exam. Okay, so when you go to the exam room, you essentially do not have any of this. Okay, so but you have to memorize those formulas. You have to memorize these formulas before you go to the exam. Okay, so but this is a good summary. Okay, so here there's kind of dashed lines where you can cut this piece of paper. You can print it out, cut the piece of paper off, and then memorize it. Put it in your pocket. Look at it every time when you go to the dining room, right? So and try to memorize it. Okay, so here it says that you have a constant linear coefficient homogeneous equation, ay double prime plus by prime plus cy is equal to 0, where the initial the leading coefficient a is not equal to 0. Consider the characteristic equation ar squared plus br plus c is equal to 0. You use quadratic formula to solve for the two characteristic roots. R12 is minus b plus minus square root of b squared minus 4ac divided by 2a, and then discuss three cases. Right, so the first case is that discriminant is positive. You have real distinct roots. R1 is not equal to R2. Then the solution is going to be a linear combination of e power R1t and e power R2t. Okay, so linear combination. If you have the complex root case, it was what we just discussed, that if you have complex root case, then the two roots are going to be complex conjugate to each other. So lambda plus minus I times mu. And then the common real part enters the exponential, the common complex part enters sine and cosine. So that will give you a solution is C1 e power lambda t is cosines of mu t plus C2 e power lambda t and sinus of mu t. Okay, so that's going to be the complex root case. Now the third case is a real repeated root case. So that means the discriminant is 0. Suppose the discriminant is 0, then the two roots are the same. If the two roots are the same, solution is going to be just the e power rt. This is what we call the golden rule, right? So you cook up solution from no solution. Okay, so from a lacking of solution, you cook up a new solution. So that's e power lambda rt and t times e power rt. You just insert a t to your second solution. You're going to cook up a new solution. So that's kind of the real repeated root case. Okay, so that's kind of the real repeated root case. So this is a kind of a general summary of those formulas that you might need for your upcoming exam. Okay, so how do you calculate? Okay, so how do you calculate this? How do you calculate this second order constant homogeneous equations? Okay, so here's I have given you quite a lot of examples in the lecture notes that you can find on Canvas. Okay, so by these lecture notes, they are meaning to help you to grasp this topic, and by practicing, you should get yourself more and more familiar with the topic and get yourself down with the familiarity of this topic. Okay, so that's kind of the, I would like everybody to practice after the class. Okay, so especially before the exam is coming. Okay, so that's you must practice. Okay, so that's kind of the thing about the homogeneous equations. Okay, so that's kind of the thing about the homogeneous equations. Okay, so now let me start to talk about non-homogeneous equations. Okay, so what does it mean non-homogeneous equation? So let us try to first review what we have been doing so far, right? So what we've been doing so far is that we considered such a constant coefficient homogeneous equation. So by prime plus c of y is equal to 0, right? So that's constant coefficient homogeneous equation. And then you're going to say that I need to just solve the characteristic equation plus c times r is going to be equal to 0, I'm going to solve for R1 and R2 and determine on the 3 cases. Like the discriminant is positive, the discriminant is negative, and the discriminant is 0. You're going to have different choices of y1 and y2. By this y1, y2, we're going to call them if you remember in the previous lecture, we're going to call them fundamental solutions. And the reason why they are fundamental solutions is because the general solution always look like C1y1 plus C2y2. They're going to be a linear combination of these fundamental solutions, right? And now, in order to have these solutions to be really fundamental, it is sufficient to take the Wronskian, W, Y1, Y2 is equal to, remember, the Wronskian has the first row are the functions, the second row are the derivatives. Okay, so the first row are the functions, the second row are the derivatives. So this is going to be very important. If the Wronskian is non-zero, let's say you check the Wronskian at just 1 point. Remember, we've been talking about the so-called Abel theorem, which says that the Wronskian has to be checked only at 1 point, right? So that it only has suffices to check the Wronskian at 1 point, right? So if at 1 point you check the Wronskian is non-zero, then this means the solution are linearly independent, right? So that's kind of a very simple business, right? So that if the Wronskian is non-zero, you're going to have a fundamental solution. So that's the notion of fundamental solution. Right, so that's the notion of fundamental solution. And the whole theory, okay, so that we've been talking about here, can be actually generalized to the case when you are going to have an equation, right? So an equation that has homogeneous but not necessarily constant coefficient. So that's just a linear homogeneous equation in a standard form, right? So PT and QT. So that's going to be a general thing that we should recognize that if you have, right, if you have 2 solutions, so y1 and y1 is a solution, and if you have another solution, right, so that's what we've been talking about in the last lecture, right, so multiplied by qt of y2 is equal to 0, so both are going to be your solutions. Then what happens here is that their linear combination c1y1 plus c2y2, you take a double prime and plus p of t multiplied by c1y1 plus c2y2, you take just 1 prime plus q of t multiplied by c1y1 plus c2y2 is just going to be 0, right? So that's going to be very simple. So that means the solution is actually a linear combination. So y of t c1y1 plus c2y2. So it's going to be a linear combination of the y1, y2. And the whole theory carries, right? So the whole theory carries means that if you take the Wronskian of this y1, y2, right? So the Wronskian is going to be y1, y2, y1 prime, and y2 prime. If the Wronskian is non-zero, then it means that the 2 solutions are going to be linearly independent, from which you can determine the C1 and C2. So that's kind of going to be a very simple business, right? So that's kind of very simple business about homogeneous equation. So this is all about homogeneous equation. By homogeneous equation, it means the term here is 0. There's no term, right? So remember, we've been talking about the classification of ordinary differential equations. I'm sure that a lot of you have not grasped it, but it's completely fine. We will review it before we take the exam, right? But you must realize that in order to have a homogeneous equation, it means that the equation do not contain a term that doesn't have the y. So all the terms in this equation are going to have the unknown variable y. There's no term that's just independent of that y. In this case, we're going to call this equation a homogeneous equation. What does that mean, a non-homogeneous equation? Okay, so non-homogeneous equation. Okay, so let's say by non-homogeneous equation, it means an equation that must take this form: y double prime plus pt of y prime plus qt of y is equal to some kind of g of t. Where the g of t is actually the so-called non-homogeneous term, right? So where the g of t is what we actually call the non-homogeneous term, right? So non-homogeneous term, and it's usually non-zero, right? So it's usually non-zero. So the point here, question here, is then how do you solve an equation with a non-homogeneous term, like g of t is non-zero? How do you solve it? Well, previously, the idea is to add two solutions, right? So for homogeneous equations, the crucial idea, right? So the crucial idea is to add two solutions, right? You have two solutions, you just add them, right? So add two solutions. But here, this situation here is that you cannot add, right? So you, let's say y1 double prime plus p of t, okay, so y1 prime plus q of t of y1 is equal to g of t, right? So that's g of t. And suppose y2 double prime plus p of t of y2 prime plus q of t of y2 is equal to g of t. Both are equal to g of t. So then can you add them? Well, if you add them, you're going to see that y1 plus y2, okay, so double prime plus p of t multiplied by y1 plus y2, just 1 prime plus q of t multiplied by y1 plus y2, you can add them. But if you add them, the right-hand side is going to be 2 times g of t. This is not what you want, because the right-hand side is now non-zero. And if you have non-zero term, you twice this non-zero term, it's not going to be itself. Right? Previously, it was good because you add that both are zero, so you can add them. You cannot really add them, right? So you cannot really add them. So what is the next operation after addition in your mathematics classes, right? So let's say you have learned addition some time ago in your math classes, and after addition, what's the next operation? The next operation in your primary school is subtraction, right? So if you cannot do addition, then why don't we do subtraction, right? So if we cannot do addition, why don't we do subtraction? So that means we cannot do addition. So let's try to do subtraction, right? So because we cannot do addition, now why don't we do subtraction, right? So if you do subtraction, you're going to see that situation is good. Because this is a linear equation, you can just subtract these two solutions and put the derivative out of the subtraction. It's completely fine. But if you subtract gt from gt, you're going to end up with 0. Right? So that's going to be a homogeneous equation. So that means if you set, okay, so if you set y1 minus y2 is equal to a capital Y is another solution, then it says that y double prime plus pt of y prime plus qt of y is going to be 0. So that's going to be a homogeneous equation. Is that good, right? That's going to be a homogeneous equation. And you know the solution of a homogeneous equation, right? So that means the y of t is actually c1 of the some kind of y1, right? So plus c2 of the y2. Where the y1 and y2, okay, so the y1t and y2t are, so they are capital Y1, Y2. So what does it mean? It means that the capital Y1, Y2, they're actually solutions of this homogeneous equations. They're fundamental solutions. So basically, you want the Wronstein of Y1 and Y2 to be non-zero. So that's kind of the solution of the homogeneous equations. All right, so that's the solution of the homogeneous equation. That's capital Y of t. So what does this whole thing tell you? Well, it tells you that let's do the following imagination. Okay, so let's do the following imagination. Suppose, okay, suppose the solutions. Okay, so let's do the following abstract imagination. Okay, so let's say suppose the solutions of the non-homogeneous equation. You have the solution of the non-homogeneous equation is lying on a plane, right? So maybe you have two solutions, like one solution is y1, the other solution is y2. They're just represented as points on the plane. Then this whole theory tells you that if y1 and y2 are the two solutions of non-homogeneous equation, then their error is going to be just the y, which is the solution of the homogeneous equation. Is that good, family? Right? So, and we know the general solution of the homogeneous equation, like what we have here. So that's homogeneous. Right? So that's homogeneous. So we know the solution of a homogeneous equation. It must be a linear combination of two fundamental solutions. So these are fundamental solutions are pertinent to the notion of homogeneous equations, right? So we know that the solution of homogeneous equation must be linear combinations of the fundamental solutions. Therefore, in order to know, let's say, in order to know any point, in order to know any solutions that is a solution to the non-homogeneous problem, it suffices to know only one point, right? Only one point on which is a non-homogeneous solution. And then the difference between this solution and the solution here is going to be just by a kind of solution which is pertinent to the homogeneous one. Is that good, All right, so that's kind of our business, right? So that's kind of our business, right? So that's kind of our business. So let me summarize this idea, right? Let me summarize this idea. The idea is the following. Suppose you start from a non-homogeneous equation. I want to have a non-homogeneous equation, y double prime plus pt of y prime plus qt of y is equal to some non-homogeneous term, g of t. I want to solve this. Now, how do I solve this equation? Well, I want to turn this equation first into a homogeneous equation. Okay, so that means y double prime plus pt of y prime plus qt, right? So of y is equal to 0, right? So y double prime qt of y is equal to 0. This homogeneous equation is the so-called complementary equation. Okay, so complementary. So this is a new terminology. Okay, so the new terminology, it is going to be called the complementary equation. So this homogeneous equation, complementary equation, so sometimes we won't use the capital Y. Okay, so sometimes we will not use the capital Y, right? So, but rather we will just call it YC. Okay, so in order to have this YC, YC just denotes for the complementary. So the subscript, the C, stands for complementary. So complementary equation means that it complements the non-homogeneous. So this is non-homogeneous. Okay, so this is non-homogeneous equation. So the complementary equation just complements the non-homogeneous equation by removing the right-hand side. Right? So that's complementary equation. So let me maybe I will use a better symbols for my complementary equation just to agree with this definition of being complementary. Okay, so that's just to agree with the definition of being complementary. So that's going to be our complementary equation is going to be called YC. Okay, so it's going to be called YC, and the complementary solution, let me say, is Y1 of C, right? So that's Y2 of C. They're going to be complementary solution. So that's Y1 of C, Y2 of C. So that's going to be your complementary. So this difference is just a complementary solution. Is it good, everybody? Okay, so that's complementary solution. Now, this complementary equation is known to be solved, right? So this complementary solution is known to be solved. It's very easy to solve this complementary solution. So the complementary solution is going to be solved as YC of T is C1 Y1 of C of T plus C2, right? So Y2 of C of T. The Y1T and Y2T are kind of two fundamental solutions of this complementary equation. So sometimes we will suppress, okay? So sometimes we will suppress this bracket C just to make it clear that they are going to be called Y1, Y2. But you must realize, okay, so you must realize that these Y1, Y2 are not solutions of non-homogeneous equation, but they are solutions of the homogeneous one, meaning that you're going to remove the non-homogeneous term in the non-homogeneous equation. Is that good for everybody? Okay, so that's called complementary equation. Now, with that complementary equation at hand, you're going to check that the wrong scheme, W, Y1, and Y2 is non-zero, just to make sure you really have these two complementary equations. Okay. So now, if we come back to the non-homogeneous equation, our heuristic is the following, that in order to determine the whole plane of solutions of non-homogeneous equation, I will just need one point on the non-homogeneous equation. Let me call it capital Y. So previously, I was using capital Y here, but now we changed our notation. We're going to use this YC, okay, YC. So that means, let me say capital Y is a solution to the non-homogeneous equation, right? So you just have one solution. Now this is like in geometry, right? So like in geometry, how do you determine a plane? Well, in order to determine a plane, it suffices to know that there is a point passing the plane, and that for any other point in the plane, it suffices to know their difference. Is that good for everyone, right? So if you know the plane and you know that all those vectors that start from that point and then go everywhere, then you form a plane. But this difference is going to be just a complementary solution. That's just going to be a complementary solution. So that means you're going to reach any solution of the non-homogeneous equation, I'm using small y, is equal to a particular solution plus a complementary solution. You see what I mean, right? So that's kind of the scene about. This is about non-homogeneous solution. Remember, let me repeat it. It says that the solution of a non-homogeneous equation consists of two parts. One part is a solution, a particular solution. So this is what we call it a particular solution. Right? So this is what we call a particular solution. So that's a particular solution of the non-homogeneous equation. Once you know the particular solution, it suffices to add from the particular solution a general solution that comes from the complementary equation. Remember, the complementary equation is homogeneous. So you know how to find the general solution. And therefore, the particular solution, the general solution, this is a general solution to the non-homogeneous problem. The general solution to the non-homogeneous problem consists of two parts. One part is the particular solution to the non-homogeneous problem. The other part is the general solution to the complementary equation. Is that good, family? Right? So that's kind of the sub-theory. So let me say the general solution. Okay, so the general solution to non-homogeneous equation, right? So the general solution to the non-homogeneous equation simply takes the form y of t is equal to capital Y of t, where the capital Y of t is what we call it the particular solution, right? So the particular solution to non-homogeneous problem, right? So the particular solution plus the yc of t, this yc of t is going to be the general solution, right? So general solution to a complementary equation. By complementary equation, it means homogeneous. So you just remove the non-homogeneous term in the non-homogeneous equation. You're going to make it homogeneous, and you're going to have a general solution to the complementary equation. So this is a very, very important. This is a very important decomposition. It's going to tell you that in order to have a general solution to the non-homogeneous equation, it suffices to find just one particular solution. So this is only one particular solution. So that means you actually do not need, presumably there are many solutions, right? But you don't need to know that many solutions. So you just need to know one particular solution. Because if you know one particular solution, then the general solution is going to be formed by this particular solution plus a general solution to the complementary equation. Is a good family? Okay, so this is a little bit abstract, but it is a very useful theory. Okay, so let's summarize this idea. The idea says that if you have two solutions of the non-homogeneous equation, then the difference is going to be a solution of the homogeneous equation. So therefore, it means that if you have fundamental solutions of the homogeneous equation, then the difference between two general solutions of the non-homogeneous equation is just a linear combination of this fundamental solution for the homogeneous equation. Is that good for everybody? Okay, so that's kind of the solutions are called complementary solutions, right? So therefore, you can summarize this idea by saying that how are we going to solve a non-homogeneous equation? Remember, here in this lecture, we're actually starting to talk about non-homogeneous equations, right? So how are we going to solve a non-homogeneous equation? Well, first of all, you just remove the non-homogeneous term. Any non-homogeneous equation must have a non-homogeneous term. So that means there is a term that do not depend on any of those y's. You must remove it, right? So let's remove it. You're going to reach an equation which you're going to call it the complementary equation, right? So the complementary equation is with a subscript C, right? So that's called a complementary equation. Now, with the complementary equation at hand, you are going to solve for it, right? How do you solve it? Well, it's very simple. Just determine this y1, y2, their fundamental solutions, and the linear combination. So this is what we know how to do it. We know everybody knows how to do this, right? So it's kind of very simple business. Now then, we're going to say that you want to just find a particular solution, capital Y, of the original equation. By original equation, it means the original non-homogeneous equation, right? So it means the original non-homogeneous equation, right? So let's say you can find a particular solution of this original non-homogeneous equation. Then what you say is that the general solution of this non-homogeneous equation is just consists of two parts. One part is the complementary solution, which is a general solution to the homogeneous equation. The other part is a particular solution of the non-homogeneous equation. By particular solution of the non-homogeneous equation, it simply means, okay, so by particular solution of non-homogeneous equation, it simply means that I just want to find one solution. Is that good, family? It doesn't make sense to have many solutions, but I just need to find one of them. Is that good, family? Okay, so then you have to be lucky. You have to be lucky in just finding one solution. Okay, so one solution is enough for you to conclude. Okay, so one solution is enough for you to conclude. Okay, so how many times of luck you need in order to find a solution for the non-homogeneous problem? Now you can see that I would say that you have to be lucky 3 times, right? Why 3 times? Because in order to determine the complementary solution, you have to be lucky twice. Remember, any complementary solution, any solution of the homogeneous problem is going to consist of 2 fundamental solutions. So there's going to be 2 fundamental solutions. Is that good, family? Right? So the 2 fundamental solutions have to be guessed. So you have to be lucky twice. Now, as long as you are lucky twice, you have to be lucky only 1 more times in order to find a particular solution of the non-homogeneous equation. Is that good, family? You just have to be lucky just once more to find a particular solution of the non-homogeneous equation. And once you are lucky the 3 times, you just combine all of them. That's going to be your solution to the non-homogeneous problem. Is that good, family? Okay. So we have reached a quite nice theory about non-homogeneous equations. Okay, non-homogeneous equation. So this is going to be a theorem. Okay, so the theorem says that the general solution of the non-homogeneous equation just consists of 3 parts. 1 part and 2 parts. The first and second part consist together is going to form the solution of the complementary equation. And the third part is going to be just one particular solution. No matter what it is, you just want to find one particular solution of this problem. That's enough. Is that good for everybody? Okay, so that's kind of the thing. Okay, so that's kind of the thing. So that's kind of the thing is that it looks like, okay, so it looks like from this whole discussion, it means that if we want to find, okay, so let's say if we want to find a solution of the non-homogeneous problem, so y double prime plus pt of y prime plus qt of y is equal to g of t. I want to solve this non-homogeneous equation. Then it suffices to first solve the complementary equation. The pt of yc prime plus the qt of yc is equal to 0. Your complementary equation is being solved. So the yc of t is c1y1, right? c1y1 of t plus c2y2 of t. So you're going to solve this complementary equation. Then it suffices to find one particular solution. So you have to find one particular solution. That's very important. Once you find a particular solution, it suffices to combine them. So it suffices to say that this is yct plus capital Y of t. So that's the whole procedure. So it looks like in order to concretely solve a non-homogeneous equation, the only thing left is that we don't know how to find capital Y of t, because we know how to find y1 and y2, for example, by our theory of characteristic equations. So therefore, it is very important to find the capital Y of t. Is that good for everybody? Okay, so that's kind of the, I mean, we are essentially extending our whole ideology of guessing solutions, because previously we have kind of formalized our theory about guessing solutions by saying that the guessing of 2 solutions form the theory of Wronskian, right? As long as you guess the 2 solutions, the Wronskian is non-zero, then you have all you need for fundamental solutions, and you can combine them to build up your general solution. So now we have extended our guessing theory by saying that in order to solve a non-homogeneous equation, I have to just guess once more. I have to guess once more in order to find a solution that's really makes sense in terms of non-homogeneous equation. And I put all my guesses together, then I'm going to have the general solution. So that's kind of we're actually building I would say, a mathematically rigorous theory for guessing solutions, right? We're not really trying to solve equations, we're trying to guess them. Is a good family. Now let me ask just one small question. Okay, so since you said that I need to find only one particular solution. However, let's say on an exam, maybe somebody is going to find one particular solution, another person is going to find another particular solution. It might not be the same particular solution. It is a very rare chance that we're going to make the same conjectures for both of us, right? So that's kind of the problem. How about two solutions, right? So for example, y1 is a particular solution, and y2 is another particular solution. They're not going to be equal to each other. Then somebody is going to say that as my solution is equal to the complementary solution plus y1 of t. And then somebody else is going to say y2 is going to be, okay, so somebody else is going to say that his solution, y of t, right? So let me say y theta of t is going to be yc of t complementary solution plus another particular solution. Then who is correct? Right? So I've guessed the two particular solutions, but who is correct? Right? So that's kind of it looks like two are both correct. Well, you must realize that if y1 is a solution, okay, so you must realize that if y1 is a solution, it means y1 plus p of t of y1 prime plus q of t of y1 is equal to g of t. And y2 is a solution, so y2 double prime plus p of t of y2 prime plus q of t of y2 is going to be another solution, right? So, and therefore it means that y1 double prime minus y1, okay, so it means that y1, okay, so it means that y1 minus y2 double prime plus p of t multiplied by y1 minus y2 prime plus q of t multiplied by y1 minus y2 is just equal to 0. Is a good family. So the difference between these two non-homogeneous equations is going to be homogeneous. So that means the y1, y2 is actually one of the solutions in the theory in the homogeneous equation. So that means y1 minus y2 is actually c1 theta of y1 plus c2 theta of y2, where the y1 and y2 are actually fundamental solutions. So that's going to tell us that you cannot difference between these two. So y theta of t is equal to y of t, right? So y of t, let's say y of t plus y1. So let's say I will write this one as, so y theta is equal to y minus y1 plus y2. So it's easy to understand because if you minus y1, you get yc, then plus y2. So that means this y is kind of y of t, right? So plus y2 minus y1. And y2 minus y1 is actually equal to y of t, right? So y of t, let's say plus, so let me use another set of constants, right? So plus c1 y1 plus c2 y2 theta. So what does it mean? It means that the two people are going to find two different solutions that just differ by a complementary solution. This is actually complementary. Right, so if it is complementary, it doesn't really matter because it means that this is nothing but, okay, so this is nothing but yc of t plus the particular solution for the first one. The first person found this particular solution, and then this is c1 y1 plus c2 y2 is going to be a complementary solution. So that's going to be means that you're going to reach another complementary solution plus the same y of t. Is a good family, right? So that's kind of the same y of t. I mean, this is y, so this is actually y1. So that kind of tells you that this solution is actually another complementary solution plus the y1 of t. I can write it this way. And that means you didn't create really two different solutions because neither you use either yc or yc theta are complementary solutions. There are many complementary solutions because the complementary solutions are the general solutions of the homogeneous equation. Is a good family? Okay, so it doesn't really matter that you find two different solutions of the same non-homogeneous problem. It's just that both of them are correct. However, on the exams, right, so in order to reach good performance on the exams, I'm not saying that you're wrong, but remember, the grader have a very limited amount of time in determining whether or not you're correct or not, right? So try to use the simple capital Y of t as simple as you can. Okay, try to make it as simple as you can. Okay, so that's the whole thing, right? So it means that our whole business is now reduced to the task of step 2, which means that here I want to find a particular solution of the non-homogeneous equation. I just want to find a particular solution of the non-homogeneous equation. How to do that? Well, here we're going to talk about 2 different methods. One method is called the method of undetermined coefficients. Another method is called method of variational parameters. So there are actually 2 different methods of determining these solutions. Okay, so the first method is called the method of undetermined coefficients. The second one is called the method of variation of parameters. Okay, by undetermined coefficients, the steps are overviewed as follows. So the philosophical idea behind the method of undetermined coefficient is as follows. First of all, you want to take a look at the right-hand side function, g of t. So by right-hand side function, it means the non-homogeneous term, g of t. Now, based on the non-homogeneous term, you started to make good guesses. You start to make good guesses on your particular solution, capital Y of t, based on the function g of t on your right-hand side. Okay, you make good guesses. The good guess on capital Y of t are usually some functions similar to g of t, but including some coefficients. So that means, so for example, g of t is an exponential, then you want to try some exponential, capital Y of t, but with the unknown constants there, coefficients, right? And then you determine the coefficients by saying, well, you have capital Y of t, it must be a solution, so that must be a solution. You put into the equation, yeah, it should be a solution, and therefore this is going to give you some kind of constraints or coefficient relations. By using that equation, from these coefficient relations, you're going to solve for the constants, and you're going to have your solution. Okay, so that's kind of the philosophical idea, how you use the so-called method of undetermined coefficients. Okay, so how you use the method of undetermined coefficients. Okay, so I will leave to next lecture to start talk about some examples, how the method of undetermined coefficients are being applied, how the methods of undetermined coefficients are being applied. Okay, so that's kind of all I want to say for today's lecture. Okay, so let's come back in the next lecture and we will continue. Okay, so see you in the next lecture.